Okay, events that have no outcomes in common are said to be mutually exclusive. So we've got a Venn diagram that looks like this. So event A and event B, and there's nothing in common. So an example would be rolling a die and tossing a coin, because, I mean, yeah, the outcomes are not going to be the same at all. So for this, when we look at the addition rule, so the probability of A union B is probability of A plus probability of B minus probability of the intersection. As we can see, we have no intersection here. That bit goes away. So this is our addition rule for mutually exclusive events. So probability of A or B is just the probability of A plus the probability of B. Okay, probability of A is 0.3, so we can fill that in here. Probability of B is 0.4, fill that in here. What are we looking for? We're looking for the probability of A or B, A union B, and we just add that to that using the addition rule. So it's 0.3 plus 0.4 equals 0.7. Next, we want to find the probability of A and not B. So that is, well, that's just here. This is the only bit that satisfies being both A and not B. So that is going to be 0.3. Okay, and the last one, probability of not A and not B. So that's something where A is not true and B is not true, and that's just this whole outside bit. So we can do that because we know the total probability of the probabilities is 1. Take away the probability of A, so 0.3, and also take away the probability of B, which is 0.4, so that's going to leave us with 0.3. Now you should have a go at the next example. Okay, events are said to be independent if the outcome of one doesn't affect the outcome of the other. So, for example, I mean, the temperature and ice cream sales will not be independent, whereas the temperature and pyjama sales probably are independent. So let's look at an example here. So we've got, these what are they? Beads in a jar, and we've got 4 red beads, 7 blue beads. So if we don't replace in this first example, then here the probability that we get pick a red on the first is 4 out of 11, and then we've got 7 out of 11. And then here, because we picked a red the first time on this strand, we're only going to have 3 left and out of 10. And here we're going to have 7 out of 10. So you can see these do depend on what happened in the first pick. So the second pick depends on what happened in the first pick. And again here, we're going to have, so we picked one of the blue ones, so we've still got 4 out of 10 left, and then 6 out of 10. And on this go, if we do replace them, then here we've got 4 out of 11, and then it doesn't affect the next one because we put it back. So again, we've got 4 out of 11 and 7 out of 11, 7 out of 11, 4 out of 11, and 7 out of 11. So this is dependent, and these are independent. Here's the test for independence. So if 2 events are independent, then probability of A intersection B is equal to the probability of A multiplied by the probability of B. Okay, let's practice using that. So we've got these 2 events, A and B, and we're told that they are independent. So that means we know that probability of A intersection B is the probability of A multiplied by the probability of B happening. So that is 1/3 times 1/5, which is 1/15. Now, because A and B are independent, that also means that A and not B are independent. So when we find A intersection not B, we can just do the probability of A multiplied by the probability of not B. So that is 1/3, and the probability of not B is going to be 1 minus the probability of B, so 1 minus 1/5. So we've got 1/3 times 4/5, which is 4/15. And finally, we're going to find probability of not A intersection not B. And again, because A and B are independent, not A and not B are also going to be independent. So this is the probability of not A multiplied by the probability of not B. So that is going to be 1 minus the probability of A multiplied by 1 minus the probability of B. So that's 1 minus a third is 2/3 multiplied by 4/5 that we found out before. So altogether that's 8/15.